Okay, hi everyone, welcome back to this video series on cryptocurrency. Peer-to-peer mining pool, P2P pool. Managed pools create the possibility of cheating by the pool operator who might direct the pool efforts to double spend transactions or inevitable. Furthermore, centralized pool servers represent a single point of failure. If the pool server is down or is slowed by a denial of service attack, the pool miners cannot mine. In 2011, to resolve these issues of centralization, a new pool mining method was proposed and implemented. P2P pool, a peer-to-peer mining pool without a central server. P2P pool works by decentralizing the functions of the pool server, implementing a parallel blockchain like system called a share chain. A share chain is a blockchain running at a lower difficulty than the Bitcoin blockchain. The share chain allows pool miners to collaborate in a decentralized pool by mining shares on the share chain at a rate of a share block every 30 seconds. Each of the blocks on the share chain records a proportionate share reward for the pool miners who contribute work, carrying the shares forward from the previous share block. When one of the share blocks also achieves the Bitcoin network target, it is propagated and included on the Bitcoin blockchain, rewarding all pool miners who contributed to all the shares that preceded the winning share block. Essentially, instead of a pool server keeping track of a pool miner shares and rewards, the share chain allows all pool miners to keep track of all shares using a decentralized consensus mechanism like Bitcoin's blockchain consensus mechanism. P2P pool mining is more complex than pool mining because it requires that the pool miners run a dedicated computer with enough disk space, memory and internet bandwidth to support a full Bitcoin node and P2P pool node software. P2 pool miners connect their mining hardware to their local P2P pool node, which simulates the functions of a pool server by sending block templates to the mining hardware. On P2P pool, individual pool miners construct their own candidate blocks, aggregating transactions much like solo miners, but then mine collaboratively on the same chain. P2P is a hybrid approach that has the advantage of much more granular payouts than solo mining, but without giving too much control to a pool operator like managed pools. Even P2P pools reduces the concentration of power by mining pool operators. It is conceivably vulnerable to 51% attacks against the share chain itself. A much broader adoption of P2 pools do not solve the 51% attack problem for Bitcoin itself. Rather, P2P pool makes Bitcoin more robust overall as part of a diversified mining ecosystem. Consensus attacks. Bitcoin's consensus mechanism is, at least theoretically, vulnerable to attacks by miners or pools that attempt to use their hashing power to dishonest or destructive ends. As we saw, the consensus mechanism depends on having a majority of the miners attacking honestly out of self-interest. However, if a miner or group of miners can achieve a significant share of the mining power, they can attack the consensus mechanism so as to disrupt the security and availability of the Bitcoin network. It is important to note that consensus attacks can only affect future consensus, or at best the most recent past 10 of blocks. Bitcoin's ledger becomes more and more immutable as time passes. While in theory a fork can be achieved at any depth, in practice The computing power needs to force a very deep fork is immense, making all blocks particularly immutable. Consensus attacks also do not affect the security of a private key and signing algorithm. ECDSA, a consensus attack cannot steal Bitcoin, spend Bitcoin without signatures, redirect Bitcoin, or otherwise change past transactions or ownership records. Consensus attacks can only affect the most recent blocks and cause denial of service disruptions on the creation of further blocks. One attack scenario against the consensus mechanism is called the 51% attack. In this scenario, a group of miners controlling the majority, 51% of the total network's hashing power, collude to attack Bitcoin with the ability to mine the majority of the blocks. The attacking miners can cause deliberate forks in the blockchain and double spend transactions or execute denial of service attacks against specific transactions or addresses. A fork double spend attack is where the attacker causes previously confirmed blocks to be invalidated by forking below them and reconverging on an alternative chain with sufficient power. An attacker can invalidate 6 or more blocks in a row, causing transactions that were considered immutable 6 confirmations to be invalid. Note that a double spend can only be done on the attacker's own transactions for which the attacker can produce a valid signature. Double spending one's own transaction is profitable if, by invalidating a transaction, the attacker can get an irreversible exchange payment or product without paying for it. Let's examine a practical example of a 51% attack. In the first chapter, we looked at a transaction between Alice and Bob for a cup of coffee. Bob, the cafe owner, is willing to accept payment for cups of coffee without waiting for confirmation, mining in a block before the risk of double spend on a cup of coffee in a low comparison to the convenience of rapid customer service. This is similar to the practice of cups of coffee shops that accept credit card payments without a signature for payments below $25 because the risk of credit card chargeback is low, while the cost of delaying the transaction to obtain a signature is comparatively large. In contrast, selling a more expensive item for Bitcoin runs the risk of a double spend attack, where the buyer broadcasts a competing transaction that spends the same inputs UTXO and cancels the payment to the merchant. A double spend attack can happen in 2 ways, either before a transaction is confirmed or if the attacker takes advantage of the blockchain fork to undo several blocks. A 51% attack allows attackers to double spend their own transactions in the new chain, thus undoing the corresponding transaction in the old chain. In our example, malicious attacker Mallory goes to Carl's gallery and purchases a beautiful triptych painting depicting Satoshi Nakamoto as Prometheus. Carlo sells the great fire paintings for $250 in Bitcoin to Mallory instead of waiting for 6 or more confirmations on the transaction. Carl wraps and hands the paintings to Mallory. After only one confirmation, Mallory works with an accomplice, Paul, who operates a large mining pool. The accomplice launches a 51% attack as soon as Mallory's transaction is included in a block. Paul directs the mining pool to remine the same block height as the block containing Mallory's transaction, replacing Mallory's payment to Carl with a transaction that double spends the same input as Mallory's payment. The double spend transaction consumes the same UTXO and pays it back to Mallory's wallet instead of paying it to Carl, essentially allowing Mallory to keep the Bitcoin. Paul then directs the mining pool to mine an additional block so as to make the chain containing the double spend transaction longer than the original chain, causing a fork below. and block containing Mallory's transaction. When the blockchain fork resolves in favor of a new longer chain, the double spend transaction replaces the original payment to Carl. Carl is now missing the 3 paintings and also has no Bitcoin payment. Throughout all this activity, Paul's mining pool participants might remain blissfully unaware of the double spend attempt because they mine with automated miners and cannot monitor every transaction or block. To protect against this kind of attack, a merchant selling large value items must wait at least 6 confirmations before giving the product to the buyer. Alternatively, the merchant should use an escrow multi-signature account, again waiting for several confirmations. After the escrow account is funded, the more confirmations elapse, the harder it becomes to invalidate a transaction with a 51% attack. For high value items, payment by Bitcoin will still be convenient and efficient even if the buyer has to wait 24 hours for delivery, which would correspond to approximately 114 confirmations. In addition to a double spend attack, the other scenario for a consensus attack is to deny service to specific Bitcoin participants, specific Bitcoin addresses. An attacker with a majority of the mining power can simply ignore specific transactions. If they are included in a block mining by another miner, the attacker can deliberately fork and remine that block, again excluding the specific transactions. This type of attack can result in a sustained denial of service against a specific address or set of addresses for as long as the attacker controls the majority of the mining. Despite its name, the 51% attack scenario doesn't actually require 51% of the hashing power. In fact, such an attack can be attempted by a smaller percentage of the hashing power. The 51% threshold is simply the level at which such an attack is almost guaranteed to succeed. A consensus attack is essentially a tug-of-war for the next block, and the stronger group is more likely to win. With less hashing power, the probability of success is reduced because other miners control the generation of some blocks with their honest mining power. One way to look at it is that the more hashing power an attacker has, the longer the fork can deliberately create, the more blocks in the recent past he can invalidate, or the more blocks in the future he can control. Security research groups have used statistical modeling to claim the various types of consensus attacks are possible with as little as 30% of the hashing power. The massive increase of total hashing power has arguably made Bitcoin impervious to attacks by a single miner. There is no possible way for a solar miner to control more than a small percentage of the total mining power. However, the centralization of control caused by mining pools has introduced a risk of for-profit attacks by a mining pool operator. The pool operator is a managed pool, controls the construction of candidate blocks and also controls which transactions are included. This gives the pool operator the power to exclude transactions and introduce double spend transactions. If such abuse of power is done in a limited and subtle way, the pool operator could conceivably profit from a consensus attack without being noticed. Not all attackers will be motivated by profit, however. One potential attack scenario is where an attacker intends to disrupt the Bitcoin network without the possibility of profiting from such disruption. A malicious attack aimed at crippling Bitcoin would require enormous investment and covert planning, but could conceivably be launched by a well-funded, most likely state-sponsored attacker. Alternatively, a well-funded attacker could attack Bitcoin's consensus by simultaneously amassing mining power, compromising pool operators, and attacking other pool operators with denial of service. All of these scenarios are theoretically possible, but increasingly impractical as the Bitcoin's network overall hashing power continues to grow exponentially. Undoubtedly, a serious consensus attack would erode confidence in Bitcoin in the short term, possibly causing a significant price decline. However, the Bitcoin network and software are constantly evolving, so consensus attacks will be met with immediate countermeasures by Bitcoin community, making Bitcoin harder, stealthier and more robust than ever. So I'm going to here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.